Yeah. So, a very good afternoon to all of you. How are you all? Did you guys remember the yesterday's topic that we have discussed? So we have discussed the disproportionation reaction and the redox balancing, right? So there are two methods to balance a redox reaction. One is oxidation number method and the other one is half reaction method, right? So yesterday I have given one equation as a homework, right? I have asked you to find out the balanced chemical equation for the given reaction using oxidation number method. So Pragati is giving me the answer. So she has done it. 2MnO4 minus plus Br minus plus H2O gives 2MnO2 plus BrO3 minus and 2OH minus. Very good. Very good, Pragati. This is the correct answer. Very good. So what about others? Others did not do the homework? Bindu, Jain, Vishimoga, Nandini, Srinidhi, Bangtoy, Siri, Yam. What about you guys? Have you done the homework? Did you get the same answer? Did you get the same answer? You guys have done it or you have forgot? Okay, let's go ahead with the question. Right, we'll go ahead with the question and we will try to get the answer. I will give you the explanation, Pragati. So you have done a great job. Very good. Hats off to you. So this is the question. Balance this equation by oxidation number method in basic medium. This is the equation. So how we have to approach this question using oxidation number method? The step one is we have to assign the oxidation number to all the elements in the reaction, right? So what are the elements? We have manganese, we have oxygen, and Br, bromine, and then the product side also we are having the same thing, manganese, oxygen, and bromine. So you all know that the oxidation state of oxygen is -2 in all the cases. And for the remaining elements, here I have found out. For manganese, it is +7, right? You all know how did we get the +7, right? So manganese is taken as x and 4 into -2 is -8. +1 is equal to 0. So x is equal to +7. So this is how you have to calculate the oxidation number of all the elements in the given equation. Okay. Then what we have to do? Then we have to check for the species who has undergone oxidation and who has undergone reduction. Right. So manganese is going from +7 to +4. So manganese is going from +7 to +4. It means that it has gained 3 electrons. Okay, it has gained. So it is an electron acceptor. It has gained. So it is an oxidizing agent. It is an oxidizing. MnO4 minus is an oxidant, which is an oxidizing agent. Okay. Then if you look for the oxidation, change in oxidation state of bromine, it is moving from -1 to +5. So -1 to +5 means you have to add +6. Then only you will move from -1 to +5, right? So 6 electrons has been lost by bromine. So who is bromine now? It is a reducing agent. Br minus is a reducing agent. So we have assigned the oxidation number to all the elements and we have found out the oxidizing agent and the reducing agent. This is step number 1. Then in the second step, what we have to do? Balance the atoms undergoing change in oxidation number. So manganese and bromine are the 2 atoms which is undergoing change in oxidation number, right? So now, if you look into the number of atoms of those 2 elements, so in the reactant side also we have only one manganese, in the product also we have only one manganese. So it is balanced. And coming to bromine, reactant side also one Br and product side also we have one bromine. So it is also balanced. Okay. So we have balanced all the atoms undergoing change in oxidation number have been balanced. Got it? So it has gained 3 electron and bromine has lost 6 electron. They are balanced. So you don't have to do anything. Go for step number 3. Find the total change in oxidation number for the entire molecule. This is step number 3. Find the total change in the oxidation number. So for MnO4 minus, we are saying that it has gained 3 electrons. Okay, it has gained 3 electrons. We have one manganese which has gained 3 electrons. So minus 3 into 1 is equal to minus 3. Then for Br minus, we have one Br which has gained, which has lost 6 electrons. So plus 6 into 1 is equal to plus 6. Okay. So now if you look into the charges carefully, the charge of the electrons gained by manganese is not equal to the electron lost by the bromine. Okay, minus 3 and plus 6 are not equal. So what we have to do? We have to go for step number 4. Balance the increase or decrease in the oxidation number by multiplying some suitable number. So what we can do? We can take manganese electrons and you can multiply it by 2. Okay, the 2 is the suitable number which we have taken. So minus 3 into 2 is equal to plus 6. 2 means it represents 2 manganese. So in the equation, I have to change this 1 manganese into 2 by multiplying by the number 2. Okay, so that I will get this charge. Then if you go for the bromine, it is already having plus 6. This is not plus 6, right? This is minus 6. Minus 3 into 2 is minus 6. So minus 6 and plus 6. The electrons lost by bromine is plus 6. And the number of electrons gained by manganese is 6. Now, both are equal. Both are equal. Okay. So, both the charges are equal. The number of electrons lost and gained are equal now. So, it is over now. Then we have to go for step number 5. Now, we have balanced the atoms. We have balanced the atoms which has undergone oxidation, change in oxidation number. And we have balanced the charges also. So now we have to start balancing the oxygen and hydrogen, right? So now coming to step number 5. Charge balance is done using adding OH minus. So why we are adding OH minus? In the question, it is mentioned that the medium is basic. Okay. So that's why we are adding OH minus. So while adding OH minus, you have to add that OH minus to the right hand side of the equation. Okay. So I'm going to add 2 OH minus here. I'm going to add 2 OH minus here. Then this, the OH minus has hydrogen, but in the reactant side, we don't have hydrogen. So to balance the hydrogen, I have to add water. Add water to balance the hydrogen and oxygen atom. Okay. So now it is balanced. The reaction after adding water, it is balanced. Right? So we have, how many oxygen we have here? 2 into 4 is 8. And here only 1 oxygen. So 8 plus 1 is 9. And here we have 2 into 2, 4. Here 3 and 2. So 9. So here also we are having 9 oxygen. And here also we are having 9 oxygen. Oxygen is balanced. And we have 2 hydrogen here and 2 hydrogen here. Hydrogen is also balanced. Okay. So now you have to go for the verification. Verification step. The last step is the verification. So you can verify by checking the number of atoms of each element, and the total charge, So if you start balancing the charges, it will be balanced. So 2 into minus 1 I have here, which is minus 2. 1 into minus 1 is minus 1. And here it is 0. So the total charge in the left-hand side is minus 3. And here 2 into 0, which is 0. 1 into minus 1, minus 1. 2 into minus 1 is minus 2. So the total charge in the right hand side is also equal to -3. So the charge is balanced. Atoms of each element is also balanced. Okay. So this is the reaction, balanced reaction given by Pragati. And it is the correct answer, Pragati. Very good. So guys, can you all able to understand? You just need to remember the steps. Okay, remember the steps to follow and apply to some questions like this and solve 3 to 4 questions. Okay, so you will get used to it and you will not make any mistakes. Okay, fine. So now let's go ahead with the last topic of this lesson, which is called as applications of redox reactions. Okay. So in the applications of redox reactions, we are going to cover 3 topics. The very first is redox reactions as the basis for titration. Second is electrochemical cell. Third is electrode potential. Coming to the first topic, which is redox reaction as a basis of titration. So what are called as redox titration? Can anyone guess what redox titrations first of all? Do you guys have any idea about this term? Redox titrations? What is meant by redox titration? Term guys, can you all able to see the screen? Can you all able to see the screen? Is it visible to all of you? Students, can you all able to see the screen? No? What about others? Is it not visible? Bindu, Nandini, can you guys able to see the screen, the PPT? Okay, okay, fine. Okay, my dear students. So the redox titration. Okay. So thank you so much. Okay, fine. Got it. Redox titration is a method to determine the strength of a reductant or oxidant using a redox sensitive indicator. Okay, what is meant by reductant oxidant? Reducing agent and oxidizing agent. So it is used to method. It is a method to determine the strength of a reducing agent or the strength of the oxidizing agent using a indicator. Indicator means if you are looking through your eyes, you can able to find out whether the reaction has happened or what is the conversion, etc. Okay, so it is a redox sensitive indicator. Okay, so let me take the setup. So in the titration, what we do, we will have a burette. Okay, so this is a burette, which is attached with a burette stand is called, this is a burette. Okay, and here we have the container, the beaker. And we are taking one solution in the burette, and that is called as an oxidant. Okay. And the compound which we are taking in the beaker is called as reductant. Okay, it is a reductant. So we are going to do the titration with this oxidizing agent or oxidant and reductant. Now what we have to do before doing the titration, we have to add an indicator. Okay. So for example, this is an indicator. So what is an indicator? What is the definition for indicator? It is a substance. Indicator is also a chemical substance that changes the color in response to a chemical change. Okay, if a chemical reaction is happening, so chemical change occurs, okay, and that will show the color change. If a chemical reaction has happened, then it will show the color change, and by seeing the color change, we can able to identify that the reaction has occurred and it has stopped at that particular point. Okay, so it is an indicator which will indicate us that a reaction has happened inside the container. Okay, it is a substance that changes the color in response to a chemical change. If it doesn't changes its colors, then we can able to find out that the reaction has not happened. Okay, so that is the job of this indicator. Now you see, I am doing the reaction. So initially, what I'm having the reducing agent in the beaker and I'm adding 1 drop of indicator. Now, after adding this indicator, I'm going to titrate this reductant with the oxidant. Okay, titration means you will open the knob of this burette. Okay, so that the solution which is present inside that, it will come inside this reductant. Okay, so just you have to add drop by drop. You have to add drop by drop of this oxidant into this reductant. So at one point, what will happen? The solution color, the reductant solution color will change. So initially, the color of the solution was kind of light blue, okay, or colorless. Now the solution has been changed to pink color. Okay, it has been changed to pink color. So it means that the reaction has happened. Got it? So at that point, you have to stop this titration. Now the reaction has completed and you have to stop the titration. So this is called as redox titration. So if we are doing the titration using oxidizing agent and reducing agent, then it is called as redox titration. Okay. So now we can note the point on the in the burette. So here we'll have a scale. Okay. So we'll note down the point in the burette. We will use the formula. We will find out the strength of this oxidizing agent and the reducing agent. Okay. So this is called as redox titration. Now the main thing that you have to note down from here is who are the oxidizing agents? Who are the oxidizing agents used in the redox titrations? I mean the compound which we are taking in the burette is called as oxidizing agent, right? So who are those oxidizing agents used in the redox reaction? There are mainly 3. The very first is potassium permanganate. So KMnO4 is taken in the burette. And the second one is potassium dichromate, K2Cr2O7. Third compound is iodine. So these 3 compounds will mainly act as a oxidizing agent. Okay, so these 3 compounds will get filled into the burette and they will act as an oxidizing agent. All right. So let's study one by one. Let me start with potassium permanganate. Okay. So potassium permanganate has pink color. Potassium permanganate is pink color. Okay. So it is already having its own color. So it is acting as an indicator here. Okay. It is called as a self-indicator. Oxidizing agent itself is acting as an indicator. So it is called as self-indicator. Okay. So KMnO4 is an oxidant as well as the indicator. Now the solution which is taken in the beaker, it is the reducing agent. Okay. So it can be Fe2 plus containing solution or C2O4 2 minus containing solution. Iron 2 plus and oxalate 2 minus. So any one of these can be the reducing agent. Okay. So now we have to start the titration. So open the knob little bit. So 1 droplet and with another will come from the burette and it will fall into the beaker and the reaction will occur. Okay. So we have KMnO4. We have KMnO4 it will have K plus ion and MnO4 minus ion, right? So it is the oxidizing agent. So the MnO4 minus ion from the burette will react with the C2O4 2 minus in the beaker, and in presence of acid, okay, in presence of acid, these three species will react with each other to form the corresponding product. And for this particular reaction, it is Mn2 plus carbon dioxide and water. Okay. So at one point, when the reaction gets completed, the color of the solution, the beaker solution, will be changed to pink. Okay, it is a pink color. So pink color is the end point. So after that, you should not add any drop of KMNO4 to it. Okay, so pale pink color shows that you have to stop the reaction at that particular point. Okay, clear? So here what is happening? The manganese oxidation state in the reactant is +7. So manganese is moving from +7 to +2. So what is this? This is reduction. Okay, this is called as reduction. And if you look into the oxidation state of carbon, so in case of C2O4 2 minus, the oxidation state of carbon is 2x minus 8 plus 2 is equal to 0. 2x is equal to 8 minus 2, 6. X is equal to +3. So here the oxidation state of carbon is +3. And in carbon dioxide, it is +4. Okay. So carbon is moving from +3 to +4. So it is called as oxidation. It is called as oxidation. So both reduction and oxidation takes place here. So it is a redox titration using potassium permanganate. Okay. Clear for all of you? Shall we go for the second oxidizing agent? Are you all ready? Any doubts so far for anyone? Praveen, Srinidhi, Vikas, Chandu. Tell me, guys. Can you all able to understand the topics and can you all able to understand the flow of the lesson? Shall I go for the second indicator? Second oxidizing agent. Yes. All right. The second compound is potassium dichromate. What it is? K2Cr2O7. So, K2Cr2O7 is not a self-indicator. K2Cr2O7 is not a self-indicator. It is filled in the beaker burette. Now, the reductant is Fe2+. Okay. Since it is not a self-indicator, I have to add an external indicator. Okay. So, that external indicator can be diphenylamine or diphenyl benzyl. So, these two are the external indicators for this particular reaction. Okay. So, then start the reaction, start the titration. So, start the reaction. So, some droplets of K2Cr2O7 will fall into the beaker and the reaction will occur. And at one point, the color change will happen. And at that point, we have to stop it. So, we have in K2Cr2O7, we have 2K plus and Cr2O7 2 minus ion. So the anion of this potassium dichromate will react with Fe2 plus in presence of acid. See here, the Cr2O7 2 minus will react with Fe2 plus in presence of acid to form Cr3 plus, Fe3 plus and 7H2. It is a redox reaction, right? So chromium oxidation state here is +6. So chromium is moving from +6 to +3. So it is reduction. And iron is moving from +2 to +3. So it is oxidation. Clear? So this is a redox reaction using potassium dichromate. Got it? This is one of the titration. This is one of the titration. The color change, the color that you observe here is blue. Okay, the intense blue color is the end point for this particular reaction. Got it? So now coming to the third oxidizing agent. Third oxidizing agent is iodine. So first of all, you have to take potassium iodide solution in a container. Okay. Then to this, you have to add the oxidizing agent, okay, or copper 2 plus, oxidizing agent or copper 2 plus. So they will produce a color, light blue colored kind of solution. Okay. So if you are adding copper 2 plus to Ki solution, it will change its color from light colorless kind of thing to blue color. Okay. So this is the first thing you have to do. So copper 2 plus is getting added to Ki. So in Ki, we have K plus and I minus, right? So the I minus ion is written here. And they are getting converted to Cu2I2 and I2. Cu2I2 and I2. So the color of the solution changes. Now what we have to do, we have to take this particular solution and we have to add a starch. You have to add some droplets of starch so that the light blue color will be changed to intense blue color. Okay. Iodine gives the intense blue color with starch. Iodine gives the intense blue color with starch. So initially we have Cu2 plus and I minus here. Then when they react with each other, we are getting Cu2I2 and I2 in the solution. So now the I2 which is present inside the solution is responsible for the color change from light blue to the intense blue with starch. Okay, once the starch is added, starch will react with this I2 and the color of the solution is changed to intense blue color. Okay, so it is because of this iodine. It is because of this iodine. So now iodine is also an oxidizing agent. So in the beaker, you can take sodium thiosulfate. Okay, and in the burette you can take sodium thiosulfate, and in the beaker you can take this copper 2 plus Ki solution and start adding the starch. Okay, the color of the solution will change to intense blue color. Color of the solution will be changed to intense blue color when you add the starch. Now, when you start doing the reaction, some droplets of sodium thiosulfate will enter into the beaker. Okay, the reaction will happen like this. So I2 which is present here in this solution will react with sodium thiosulfate. Sodium thiosulfate formula is Na2S2O3. So when you dissociate this, you will get 2 Na plus ion and S2O3 2 minus ion. So the S2O3 2 minus ion from sodium thiosulfate will react with I2 and they will produce I minus S4O6 2 minus. Okay. So once the reaction occurs, this is the end point you will get. Okay, this is the end point you will get. So is it clear to all of you? Is it clear to all of you? So once you add the starch, you will have dark blue color and because of the presence of iodine. And if iodine reacts with the thiosulfate ion, the color change will happen from intense blue or dark blue color to light blue again. Okay, because of the formation of this I minus and S4O6 2 minus. Okay, so this is all about the redox titrations. Redox titrations and the oxidizing agents that we use in redox titration. Okay, so now let's go for the second topic of today's session, which is electrochemical cell. So what is meant by electrochemical cell? So electrochemical cell is a device which are used to convert electrical energy into chemical energy and chemical energy into electrical energy. It is vice versa. Okay. Electrochemical cell is a device which is used to convert electrical energy to chemical energy and vice versa. Okay. So now the electrochemical is getting classified into two. There are two types of electrochemical cell. One is galvanic cell or voltaic cell and the other one is electrolytic cell. Okay. So what is galvanic or voltaic cell? So we have two separate beakers and the electrodes will be dipped inside the beaker. Okay, one is an anode and the other electrode is a cathode. And there is one connection between these two beakers. And that connection is called as salt bridge. And this particular setup is connected to a circuit. And if you switch on, the reaction will happen. Okay, and it will take place. The reaction will take place. So we have two different types of chemical substances in two beakers. So here I have zinc nitrate. Here I have zinc nitrate. And here I have copper nitrate. Okay, here I have copper nitrate. Copper nitrate inside the solution. Zinc nitrate and copper nitrate. So here the chemical energy of a spontaneous redox reactor is getting converted to electrical energy. So here in case of galvanic cell, chemical energy is getting converted to electrical energy. But if you go for electrolytic cell, so in electrolytic cell setup, we take only one beaker. Okay. So both the electrodes, anode and cathodes, are dipped inside this one beaker. And those electrodes are connected with the battery. And again, we have one salt solution here inside the beaker. So salt means it will have cation and anion, right? So all the anions will move towards anode, which you can see here, and all the cations will move towards cathode. So this is the setup of electrolytic cell. So here what happens, the electrical energy is used to carry out a non-spontaneous redox reaction. Okay, electrical energy is used to carry out a non-spontaneous redox reaction. Okay, so here chemical energy is getting converted to electrical energy, and here electrical energy is getting converted to chemical energy. Okay, it is a non-spontaneous redox reaction. Okay, so I cannot say that electrical energy is getting converted to chemical energy. It is electrical energy is used to carry the reaction here. And here it is spontaneous and non-spontaneous. Spontaneous means the reaction will happen on its own. You just need to start the reaction. Okay, it keeps on going. But non-spontaneous means each and every time you have to start the reaction. Then only it will happen. Okay, then only it will happen. Each and every time you have to switch on the thing, and then only the reaction will happen. Okay, then only the anions will move towards anode and cations will move towards cathode. Okay, so these two are the electrochemical cells. Got it? So now coming to the third topic. Third topic is electrode potential. So what is meant by electrode potential? What is meant by electrode potential? So here in this picture, you can see that I have a beaker and one electrode is dipped inside it, and the solution inside the beaker, I have a zinc nitrate solution. Okay. And we have one electrode, right? So it has some ions. It has some ions. So we have an electrode and this solution is called as an electrolyte. The solution is called as electrolyte and this is called as electrode. This is called as electrode. So there will be the potential difference developed between these two. There will be some potential difference developed between electrode and electrolyte, and we call that potential as electrode potential. Okay. So electrode potential can otherwise be called as electromotive force. Electrode potential is also called as electromotive force. Okay. So there is some potential difference developed between this electrode and electrolyte, and that is called as electrode potential. Okay. So now let me talk something about anode. Solution will have some potential and that is called as solution potential. Okay. And the metal will have some potential which is called as metal potential. So in anode, metal potential will be greater than the solution potential. Metal potential will be greater than the solution potential. Okay. So zinc is the metal. Okay. Zinc is the metal. Electrode can be made of zinc. Zinc is a metal. If it loses 2 electrons, it will be converted to zinc 2 plus. Okay. So here the metal potential is greater than solution potential. So the E oxidation, you can write the E What is meant by E? Electrode potential or electromotive force. Okay. It is written for oxidation because zinc is getting oxidized, right? So zinc is moving from 0 to +2. So you can write the oxidation potential for this particular reaction. And at cathode, what happens? Solution potential will be greater than metal potential. Just the opposite. In cathode, what will happen? Solution potential will be greater than metal potential. So what will happen? The zinc 2 plus will gain 2 electron and it will be converted to zinc. So zinc 2 plus is getting converted to zinc 0. So it is called as reduction. So you can write the E reduction, electromotive force of reduction for this reaction. Okay. So now according to IUPAC, we have an IUPAC thing, right? International Union of Pure and Applied Chemistry. So those people, according to those people and their convention, standard reduction potentials are now called as standard electrode potential. The standard reduction potentials are called as standard electrode potential, which is very, very important. It is very, very important. Okay. Is it clear to all of you? So if the metal potential is greater, then it is oxidation. If the solution potential is greater, then it is reduction. Nowadays, reduction potentials are called as standard electrode potential. So what is the difference between standard electrode potential and electrode potential? Electrode potential means it is just E. It is just E, which you can see here. Standard electrode potential means you have to put E naught. You have to put E naught. Clear? So this is the difference. At standard temperature and pressure condition, if you take the potential value, it is called as standard electrode potential, which is equal to standard reduction potential. All right. So now let me talk something about standard hydrogen electrode. It is called as SH electrode. Okay. Standard hydrogen electrode means you have to take the standard condition. Standard temperature and pressure are 298 Kelvin and 1 bar pressure. So take a beaker which has a solution of 1 molar. Okay, 1 molar solution is taken here. 1 molar H plus solution is taken. And this is the setup. We have a bulb kind of thing. And there is a pressure of hydrogen, which is 1 bar here. And inside this setup, we have a platinum rod dipped into it. And here we have a metallic block. Here you can see the metallic block, right? So it is attached. And this is the thing happening inside that metal block. Okay. So let me show you the reaction. So two reactions will happen. Okay. So that metal is a platinum metal. This metal block is a platinum metal block. So here what is happening? Hydrogen is passed through this hole and it is coming inside this. So hydrogen loses 2 electrons when it comes inside. So all of you can able to see the electron, right? So when it comes inside, hydrogen loses 2 of its electron. Okay. So if H2 is getting converted to H plus, it is called as oxidation. Okay. So the oxidation potential is 0 volt for this hydrogen. And H plus, which is already present inside the solution. H plus is already present inside the solution, right? So that is taking those 2 electrons which has been lost by this hydrogen, okay, which has been lost by this hydrogen, and it is getting converted to H2. So hydrogen is moving from +1 to 0. Okay, hydrogen is moving from +1 to 0 and the E naught value is 0 volt. E naught value is 0 volt. So for a standard hydrogen electrode, the E naught value for both oxidation and reduction potential is equal to 0 volt. Got it? So this is the thing you have to keep in mind. Now let me go for the determination of standard electrode potential of metal. So how they are detecting the standard electrode potential for different metals? So for hydrogen, I have shown you. What about for other metals? How they are determining? They are determining using a setup like this. Okay, so we have a metal rod dipped inside the solution in a beaker. The concentration of the ion is 1 molar here. And also I have second beaker. which is a setup of standard hydrogen electrode, and these two are connected. Okay. And the E naught value, that is the standard reduction potential value, is measured from this instrument. Okay. So from that only we are getting the E naught values for different metals. Okay. So it will change if I change the metal rod. If I have zinc, it will show some value. If I take silver, it will show some other value. Okay. So if I change the metal, the E naught values will also change. So by taking the E naught values using this particular setup, okay, by taking the E naught values, we are getting a series, an electrochemical series for all the metals. Got it? So these are the metals at the top from lithium to lead. And after this, we have standard hydrogen electrode. And below this, I have copper, mercury, silver, and fluorine. Copper, mercury, silver, and fluorine. So the E naught value is calculated based on the standard hydrogen electrode. It is calculated based on this standard hydrogen electrode. And above the standard hydrogen electrode, we can able to see the negative values. And below this standard hydrogen electrode, we have the positive value. Okay. So if the E naught value, if the E naught reduction value is moving from negative to positive, then the oxidizing nature increases. And if it is going towards negative side, the reducing character increases. So this is very important point. The point is, if the E naught value is positive, it is a strong oxidizing agent. Value is negative, then it is a strong reducing agent. So here you can see that the E naught value of fluorine is higher. It is having plus 2.87. So fluorine is a strong oxidizing agent. Okay. And here lithium. Lithium is having the least value, minus 3.05. So it is a strong reducing agent. So mostly all alkali metals will fall here. Okay, all alkali metals will act as a reducing agent, and fluorine, silver, mercury, copper, they are acting as a strong oxidizing agent. This series is called as electrochemical series. Okay, you don't have to memorize the. They will give the values in the question. You just have to find out the answer. Okay, I will solve one question based on this concept. Don't worry. So do you have any doubts from this? Positive means oxidizing agent. Negative means reducing agent. So clear, right? Shall I go for the next? Shall I go for the next few points of this lesson? Do you have any doubt? Do you have any doubt so far here? One of you please reply me soon so that we can complete it very fast and get ready for the next class. Do you have any doubt so far? Any doubt from electrochemical series? Jainvi, Shimoga, Nikita, Nandini. Okay, thank you, Pragati. Listen. The next is the selection of oxidizing and reducing agent. How will you select? Let me take two reactions. One is with the silver, another one is with chromium. Silver plus and chromium 3 plus. And this is the table which we have seen now. Okay. So silver is having plus 0.80 value. And chromium is having minus 0.74. Okay. If the reduction potential is higher, higher will be the tendency to get reduced and better is the oxidizing agent. Right? So among silver and chromium, silver is the strong oxidizing agent. It will undergo reduction. Okay, oxidizing agent will undergo reduction. Okay, the same thing. If the E naught value is higher, higher means if it is positive, then it is a strong oxidizing agent. Okay, so in the same way, lower the reduction potential. Lower means negative. The E naught value is negative, then it is a strong reducing agent. It is a better reducing agent. So chromium will undergo oxidation. Okay, the same point. Now the last point is reactivity of a metal. Let me take the same two reactions, the silver reaction and the chromium reaction. Silver is having positive value and chromium is having negative value. If the reduction potential is lower the reduction potential, that is, if the reduction potential is more negative, higher will be the reactivity. Higher will be the reactivity. So if I compare chromium and silver, chromium is having the more negative value. So the reactivity of chromium is more. Reactivity of chromium is more. So if the E naught value is more negative, then reactivity is also very high. Reactivity is increasing. All right. Clear? So these are the points you have to keep in mind. And let us solve one question based on this concept. Given the standard electrode potentials, arrange these metals in their increasing order of oxidizing power. Can anyone give me the answer for this? We have the E naught values in the question for all four couples. You can use the concept I have taught you. What was the concept? If the E naught value is positive, then it is a strong oxidizing agent. If the E naught value is negative, then it is a strong reducing agent. So please use this concept and find out the answer, which is the correct order. We have copper, iron, zinc, and chromium. So among these four, copper is having the positive value. So it is the strong oxidizing agent. It is the strong oxidizing agent. Okay. So which element will come next? Which element will come next? The least negative. Least negative is iron, right? Iron is having minus 0.44. So that will come. Then chromium. Yeah. After this, you'll have chromium and the more strong reducing agent is very good, Pragati. It is zinc. It is zinc. So we know that higher the electrode potential, higher will be the oxidizing power. So copper is more oxidizing compared to iron, then chromium, then zinc. Okay. So this is the decreasing order of oxidizing power. This is the increasing order of oxidizing power. But anyway, both are correct only. Okay. Both the orders are correct. So with this, the lesson is getting over. Let me summarize the today's topic alone. So we have started with redox titration and we discussed about the three oxidizing agent. And I have discussed about the two types of electrochemical cell, right? One is galvanic cell and the other one is electrolytic cell. And also we have discussed about the electrode potential. Okay, electrode potential means the E value. And standard electrode potential also we have discussed, which is E naught. And then the last point is, if the reduction potential is higher, then it is a strong oxidizing agent. If the reduction potential is lower, if it is negative, then it is a strong reducing agent. Okay. So this is all about today and about this lesson. So with this, the lesson is getting over. Okay. So today we are completing the redox reactions lesson here. Do you have any doubts from this lesson? Do you guys have any doubts from this lesson? Any doubts from today's session, students? Do you have any doubts from today's session? Oh, okay. So kindly go through the lesson, revise it once again. If you're getting any doubt, please bring your doubts to me in the upcoming classes. Okay. So from next class onwards, we will start with the new lesson. We'll start with an organic chemistry lesson. Okay. Thank you so much. Thank you for attending the today's lecture. So try to join on time from next class onwards. Okay. Thank you. Take care. Bye-bye.